We've already touched on ethers in several videos. They've been our useful aprotic solvents in several of our reactions. But I thought it was about time that we actually devoted a video or two to ethers. And like all things that we've done in organic chemistry, a good way to familiarize ourselves with the molecules and how they look is to actually name them. So let's do a couple. And the first few you've seen already. So let's say we have this molecule right here. This molecule right here. What I'm going to do is I'm going to teach you two ways to name it. The common name, and that's probably the more important one, especially with ethers, because, as you can imagine, that is the more common name. That is what people say. And then I'll also show you how to name it using the IUPAC name. So let me write this down. IUPAC name, which is the International Union of Pure and Applied Chemistry, and they come up with kind of the official naming protocols for all of these organic molecules. And this is actually the convention that we used earlier when we did the alkanes and the alkenes. But in the case of ethers, the common name is more common. So the common name for this molecule right here, you look at the two carbon groups here. So let's see, you have this one right here. That is an ethyl group. That's an ethyl group right there. You have 1, 2 carbons. And then you look at the other carbon group right over there. That's also an ethyl group. You have 1, 2 carbons. So you call this, let me just write this down. That is also an ethyl group. So the common name for this is just diethyl ether. Diethyl ether. And the ether tells you, this part tells you that you have an oxygen in between your two ethyl groups. This is the common name. This is the common name. Common name. Now, the International Union of Pure and Applied Chemistry official name for it, you kind of do something similar to how we named other things before. You look for the longest chain. Let me redraw it. You look, so maybe on the left-hand side, I'll do the common names. On the right-hand side, I'll do the IUPAC names. So let me redraw what the common name of the diethyl ether. Well, you look for the longest chain. In this case, there's two longest chains. There's this one that has 1, 2 carbons, and then you have this one that has 1, 2 carbons. So you could pick either one. I'll just pick this one as the main chain right over there. It has 2 carbons, no double bonds. It is an ethane. It is ethane. And then you say, okay, I have this alkoxy group. And we call that, we put the oxy at the end of it because it has this oxygen right here. But it's the alkyl part of it has 2 carbons, 1, 2. So we call this right here, we call this ethoxy. Ethoxy. So one other way to name this, we have this ethoxy group attached to the 1 carbon. We're just going to start numbering on this side of the ethane, just because that's where the group is, attached to the 1 carbon. So we call this 1-ethoxyethane. So this is 1-ethoxyethane. You'll almost never see it actually named this way, even though this is the official name. You're much more likely to see this as diethyl ether. And at least in my brain, this resonates a lot more. You just say, what are the two groups? And you throw the ether at the end. You know that there's an oxygen in between. Let's do a couple more of these. So let's say I have this molecule right here. I have this molecule right over here. The common way is you look at the two groups on either side of the oxygen. So this right here, let me do this in a different color. This group on the left right here, we have 1, 2, 3 carbons. It's a propyl group, but we're attached to that middle carbon. So this is an isopropyl group. Isopropyl group. And on the right-hand side right here, we just have 1 carbon. So this is right here. I keep using that blue. This right here, this is a methyl group. This is a methyl group. So the common way of naming it, you just list both of these groups, and then you write ether. And you list them in alphabetical order. I comes before M. So this is, the common name is isopropyl methyl, isopropyl methyl ether. Isopropyl methyl ether. Now, if we were to do the IUPAC naming, we look for the longest carbon chain. Let me redraw the molecule itself. So let me redraw the same thing right there. So what's the longest carbon chain here? Well, we have 1, 2, 3 carbons right there. We only have 1 carbon right there. So this thing right here is our longest carbon chain. It has 3 carbons on it, so it is, and it had no double bonds. So eth, meth, propyl, or it's actually propane. So this is our longest. So we write propane right there because we're using the IUPAC naming mechanism. And then we look at this methoxy group right here. And I call this a methoxy group because I have the O that gives us the oxy, and I just have a methyl group right here. So this is methoxy. Methoxy. You remember that meth is the prefix for just having only one carbon. We add the oxy because that oxygen is there. And it's attached to the 2 carbon on the propane chain, no matter what direction you start naming from or numbering from. 1, 2, 3. So this is 2-methoxypropane. 2-methoxy 2-methoxypropane. Let's do another one. Let's do one more. And I think you'll get the gist of at least the reasonably simple ethers to name. So let's put a ring over there. And then that's attached to an oxygen. And then we have another carbon chain right here. And then we have another carbon chain right there. Let me just copy and paste that so that I don't have to redraw it. So let me copy and paste. All right. So let's do the common name first. That always tends to be a little bit more fun. So on this side, we have 1, 2, 3, 4, 5, 6 carbons in a cycle. This right here on the left-hand side is a cyclohexyl group. Cyclohexyl group. This on the right-hand side, we have 1, 2, 3. This is just a straight up propyl group. Propyl group. And so when you name the ether, you just put these 2 groups in alphabetical order, and you add an ether at the end. So it's cyclohexyl. C comes before P. So it's cyclohexyl propyl. Let me get that shade of yellow right. Cyclohexyl propyl ether. Cyclohexyl propyl ether. Now let's do the IUPAC way to name it. So you look for the longest carbon chain here. In this case, it's going to be the cyclohexane right here. We have 1, 2, 3, 4, 5, 6 carbons there. We only have 1, 2, 3 there. So this is kind of our backbone. So we write down cyclohexane. Cyclohexane. No double bonds, so it's a hexane. So that's the cyclohexane right there. If you just had these 3 carbons, it would be a propyl. But this is not just 3 carbons. It's 3 carbons and then an oxygen. So we would call it a propoxy. So this is propoxy group. Propoxy. And you don't have to number it because it can just be attached to any of these carbons. It would essentially be the same molecule. So you could just call this propoxy cyclohexane. Propoxy. Let me make it a little bit closer to the cyclohexane. Propoxy cyclohexane. But once again, the common name is what you're more likely to see. Now that we've named a few of them, let's think a little bit about their properties. So what we've seen already is that, and we've used it several times, especially in our SN2 reactions and things like that, places where we didn't where we didn't want protons floating around, we used actually diethyl ether. And in general, ethers do make for good solvents. They tend to be fairly unreactive. So good solvents, especially when you're looking for an aprotic solvent. Remember, aprotic means you don't have hydrogens that can kind of lose their electron to maybe an electronegative atom like an oxygen, and then the proton just floats around and then can go and react with other things. This does not have any hydrogens directly bonded to an oxygen in any of these cases, so it is an aprotic solvent. And because it doesn't have any hydrogens bonded to the oxygen, you also have no hydrogen bonding. And just as a bit of a review, you know that in water you have this situation. Let me draw some water molecules. In water you have this situation where the oxygen hogs the electron, so it has a partial negative charge. Hydrogen gets its its electrons hogged or taken away, or it spends less time with them, so it has a partial positive charge. So this oxygen will have a partial negative charge. And so the hydrogens with the partial positive charge are attracted to the oxygens with the partial negative charge. And you have this hydrogen bonding. And this hydrogen bonding makes water, it pulls the molecules together. So you need to put more energy into it for it to either melt or for it to actually boil and for the molecules to kind of get ripped away from each other. And that's also true with alcohols. Alcohols only have one hydrogen to each oxygen, but they still have the hydrogen bonding going on. In the case of ethers, there is no hydrogen bonding. I'll represent each of the carbon chains with an R and an R. I'll write R prime right here to show that it could be a different carbon chain than this right here. And the R stands for radical, not to be confused with free radical, completely different things. This R just means really a carbon chain attached to this oxygen. But here there's no hydrogen getting its electrons hogged by oxygens with partial positive and partial negative charges. So you're not going to have that type of hydrogen bonding. And because of that, ethers have much lower melting and boiling points. It's much easier. You have to put less heat into the system for these molecules to break away from each other because they aren't attracted to each other as much.